Well, to continue with our discussions on the partial molar properties, I ended the last class by deriving in this particular equation when I had derived the Gibbs-Duhem equations in terms of partial molar properties. Now, as I mentioned, this particular equation is something very important. So, let us first discuss, before anything else, I would like to discuss the importance of the Gibbs-Duhem equation. Of course, in this particular case, I had denoted my property with the value of m. Just keep in mind that what I was telling in terms of n, the same thing I have shown in terms of m here. So, mi bar is my partial molar property. Now, from this particular equation, there are a large number of things that we can see. For example, let us start with a binary mixture. What is it? X1 for a binary mixture plus X2 dm2 bar equals to 0. I can also write it down as dm1 bar equals to minus n2 by n1 dm2 bar, which is nothing but equal to minus x2 by x1 dm2 bar. So, from this what do we find? We find that if x2 by x1 is large, then a small change in this will correspond to a large change in this, number 1, right. So, therefore, we find that the changes in the partial molar properties, they are not independent, they are dependent upon the mole fractions. So, therefore, we find that if x2 by x, so therefore, if I have a large proportion of x2, then a small change in dm2 is going to bring a large change in dm1, number 1. Number 2, what do we find? X2 by x1 is always positive. So, therefore, an increase in the partial molar property of component 1 leads to a corresponding decrease in the partial molar property of component 2. Or in other words, as I have mentioned here, dm1 if is positive, dn2 can be negative, fine. And the most important thing is that it is very difficult to find out the partial molar properties. So, therefore, this equation gives us a way by which if I know the variation of dm1, I would be in a position to find out dm2. On integration, it will give me m2 bar for any particular composition x2, right. So, therefore, how do we go about doing this? Suppose my m1 bar is known, say, right. I would like to find out my m2 bar. I do not have a very straightforward experimental way to find this out. So, therefore, can I not write it down as dm2 bar? This is equals to minus integral x1 by x2 dm1 bar from 0 to m1 bar, or in other words, from this integration what do I get? This is equals to minus integral 0 to m1 bar x1 by x2 dm1 bar. So, therefore, from here what do I get? From here I get that if I know dm1 bar, how it varies with composition, I shall be in a position to find out m2 bar. And the important thing is, for each m2 bar, it can be estimated from the method of intercepts. Firstly, just apparently, if you just look at the expression, what is m bar, mi bar? This is del m del ni at t p n j, fine. So, therefore, it automatically implies that if you have any particular graph where your the total property m that varies with the mole numbers ni, say suppose it has a graph of this sort, suppose m equals to volume. So, suppose what I do, I keep on adding for component I or for component A, say I keep on adding moles of A, say 1 mole, 2 mole, 3 moles, 4 moles, I keep on adding, and for each particular addition I start finding out the increase in volume, right. Accordingly, I can find out different points on this curves, I can construct this particular curve. Now, if I want to find out the partial molar volume at some particular composition, say at this particular composition, what do? I can simply draw a tangent and find the slope of this curve. But finding out the slope of this curve in this particular way, it is not at all a very easy technique. Okay. It leads to a large number of errors. So, therefore, the proper way or a much more accurate way of finding out the partial molar properties, the experimental determination, that is usually done, determination of mi bar. The usual method is known as the method of intercepts. Let us see what is this method first, and then we will see how it works. Now, definitely you must remember that direct numerical differentiation, just I was telling, this can be done that, but this is not very accurate. So, therefore, this method of intercepts has been adopted. Now, what is this method of intercepts? We know that the molar volume of a mixture. What is this? This is nothing but the, again we use it for a two component system, say component A and component B. What is V? This is equals to Na plus Nb. I can write it down, or in other words I can write it down as V into Na plus Nb. Agreed. What is Va bar equals to by definition? It is del V del Na at constant Tp Nb in this particular case. So, this should be equal to differentiation of this. So, therefore, this should be del Na of V into Na plus Nb at constant Tp Nb. On differentiating, what does this give you? This gives you V plus Na del V del Na Tp Nb plus Nb del V del Na Tp Nb, right, because del Na del Nb gives you 0. So, therefore, what is this? This is equals to V plus Na plus Nb, that is the total number of moles, into del V del Na at Tp Nb. Agreed. Now, from chain rule, let us see if we can simplify this a little more further. What is this? Let us see, del V del Na at constant, what have we done? This is at constant Nb, and Tp, of course, it remains constant. So, therefore, can we not write it down from chain rule as del V del Xb at constant Nb del Xb del Na again at constant Nb? This is possible. What is this? Tell me, is this not equal to del V del Xb at constant Nb into del Na of Xb is nothing but Nb by N plus Nb? And what does this give you? Is this not equal to minus of del V del Xb into Nb by Na plus Nb whole square? Simply differentiation, that is what I am doing, nothing else. So, from here, what is this equal to? From where did we start? Now, this particular equation, suppose I substitute it here. So, therefore, what do I get then? Then I get, this is Va bar, the equation Va bar was equal to V. If I just write down the equation, this is V plus Na plus Nb into del V del Na Tp Nb, right. So, if I substitute this particular part from here, then what do I get? In this particular case, I get V A bar, this is equal to V minus Xb, because Na plus Nb whole square and this cancels out, del V del Xb, I get this. So, therefore, Va bar is this. So, suppose now suppose I have got suppose I so suppose I have plotted in this particular case. What have I done? In this particular case, I have plotted the volume of the component, the molar volume of the component as a function of its composition, right. So, from there what do I have? I can very well write down this particular equation as V equals to V A bar plus x b del V del x b. I can write it down. In the same way, if I had started with component B and not component A, then I would have landed in an equation as V b equals to V plus 1 minus x v del V del x b, from where I know this V would have been equals to V b bar minus 1 minus x b del V del x b. Sorry, very sorry, V, no, sorry, it is all right, V equals to, right. Now, from this equation and this equation, what do you find? We find that suppose we are plotting V versus x b, the thing which I have done in this particular graph. We have plotted molar volume as a function of x b or x 2, whatever it is, right. And we would like to find out the partial molar volume at say some particular, say very sorry, at some particular point, say at x 2 equals to 0.3. Suppose I would like to find out. So, this is the point. At this particular point, I would like to find out the partial molar volume. What do? I draw a tangent to the curve. And from this equation, what do I find? From this particular equation, we find that at x b equals to 0, what is V equals to? V equals to. So, therefore, this reduces to the partial molar volume V equals to V A bar under what condition? When x, yeah, V equals to V A bar for x b equals to 0 and V equals to V b bar at x b equals to 1. Isn't it? Just check it up. This is the thing that you are supposed to get. So, therefore, the thing which we do is we simply draw the tangent and then we find the intercepts on the two extreme axes. And once we find the intercept, we know that merely from the intercept at x 2 equals to 0, that gives us the partial molar volume of component A or component 1, and the intercept at x 2 equals to 1, that gives us the partial molar volume of component 2. So, therefore, this is one particular way of finding out this experimental way of finding out partial molar volume of any of the components. And then again I would like to remind, suppose you are finding just the partial molar volume of any particular component, the other component can be found out from Gibbs-Duhem equation. So, therefore, what are the things that we discussed? We first understood what is partial molar properties. We discussed the characteristics of the partial molar properties, and we also found out the how by the method of intercepts, merely from experimental data, partial molar properties can be evaluated. Now, before I end, there is one particular partial molar property which is particularly important. We continued our discussion with the partial molar volume just because it is easy for us to understand and to imagine that particular quantity. But the partial molar property which is going to be of importance to us is the partial molar Gibbs free energy G I bar. What is this equal to? This is equal to del G del N I T P N J not equal to I. And we have already defined this is nothing but equals to mu I. And again, just the way that we had discussed earlier, in the same particular way, it can very well be defined that dg equals to, we can define it in this particular way. This is nothing but at constant temperature and pressure. So, this will be sigma Ni T P N J not equals to I, right, into your dNi. So, therefore, here we can write it down as sigma mu I dni. This can be written down, where again mu I, this is a function of Tp. For binary mixtures, it is a function of n1 n2, otherwise it is a function of ni, if we have to deal with in this particular way. Again we find out that this particular term, this does not only show how your Gibbs free energy varies with mole numbers. If we can write this equation in this particular form and then we differentiate du equals to, if we elaborate this particular differentiation and say okay, I will just do it for you, minus pdv, sorry, minus vdp plus sdt, we are just differentiating it, plus again that dg term comes. So, therefore, for dg we have vdp minus sdt, plus if it is a binary mixture, we have just two terms mu b. Agreed. Now if we cancel out the terms, this term, this term, this term, this term, if all of these they cancel out, then in that case what do we get? We get du equals to minus pdv plus tds plus mu a dna plus mu b, just the way we had done for our pure component systems. So, therefore, at constant v and s, what do we know? Du is nothing but equals to sigma mu I dni. Fine. So, again in the similar way, if we continue, what do we find? We find mu I, therefore, it is del g del n I at constant T p n j not equals to I. This is equals to del u del n I at constant S v n j not equals to I. This is equal to del h del n I, just the way, but we have just added this particular term, and in terms of Helmholtz free energy, it is T v n j not equals to I. So, from there we find that this particular term, it is not only the partial molar Gibbs free energy, but it also shows how other thermodynamic properties, they vary with change in composition under different interactions between the system and the surroundings. So, therefore, mu I occupies a unique position. Just because of that, we do not apply any sort of bar or anything on it, we just keep it as mu I for component I in solution. For a pure mixture, we simply denote it by mu. This is sufficient for you to remember. The other thing which is of importance in this particular case is that we very well know that dg equals to minus dw non PV. This also we had defined under some particular conditions. So, therefore, what does this imply? This implies this is equals to Na d mu a, or in other words, if I write it in general, it is Ni d mu I. So, from this what do we deduce? From this we can deduce that suppose we can also bring about some particular change in the partial molar properties, which gives us a change in the total, or rather we can suppose in an electrochemical cell we can perform reactions at two different sites, due to which the mole fractions or the compositions of the mixture can change, and from there we can derive some amount of non PV work, which will be a function of the chemical potential. So, therefore, chemical potential, in that case we find therefore that it has got some very special significance as compared to the chemical potential of. So, we can just write it down that mu a dna plus mu b dnb, just repeating what I have said, this is equal to dw non PV. So, therefore, from here it implies that additional non PV work can be done just by changing the composition of the system, and this is what is practiced in an electrochemical cell. where chemical reaction is arranged to take place at two distinct sites at the two electrodes, and the electrical work that the cell performs can be related to its changing composition or to its changing the changing of the chemical potential of the reactants, right. So, therefore, this was all about partial molar properties. We have defined a large number of partial molar properties, and from there what have I told you? We have come to know that from these partial molar properties, they have some particular relationships, they obey all, they have all the characteristics of total properties and molar properties. We have found out their experimental determination. The only question which I keep before you, which we will be discussing in the next class, is whatever properties we have defined that they have an additive characteristics, all other properties. Does partial molar fugacity have identical properties, or does this have some unique characteristics of its own? Think about it. We are going to deal with partial molar fugacity in the next class, how it is unique as compared to other partial molar properties, and this is of special concern to us because we started discussing partial molar properties just because we wanted to find out the fugacity of component I in a solution, and from there the entire problem started. So, therefore, it is very important to understand the partial molar fugacity of component I in solution. We will be dealing with this in the next class. Thank you very much.